In this session, we're going to see quadratic functions, and then we're going to look at them through the lens of transformations. First, we'll define a quadratic function is a function whose defining expression is a degree 2 polynomial. Here's an example. F of x equals ax squared plus bx plus c. I guess that's not really an example. It's just a generic one. This expression can be converted to an expression f of x equals a times the quantity of x minus h squared plus k by completing the square on x. The value of this is we can use h to figure out a horizontal translation to the left or to the right. We can use k to figure out a vertical translation up or down. And then the value of a will indicate a vertical stretch or compression and the orientation, depending on if a is positive or negative. As a brief illustration, suppose we have just a set of axes here, and here's just a quick sketch of a quadratic function. It's a parabola, and we know that the vertex of the parabola is at hk, and that's due to what we know about translations. There exists something called an axis of symmetry. This is a line that divides the parabola in the middle. The vertex is on the axis of symmetry, and the graph is symmetric to the left and to the right of this axis, hence the name. Every quadratic function has a y-intercept somewhere. And being on the y-axis, the y-intercept is going to have, it's going to look like 0b, let's say. And some of them have x-intercepts, some of them don't. It all depends on the orientation of the parabola and the vertex in relation to the x-axis. In this session, we're going to see how to sketch graphs of quadratic functions. We're going to find the vertex. We're going to find the axis of symmetry. And we're going to find as many intercepts as we can. That is, wherever they exist. And remember, for an x-intercept, y is 0. For a y-intercept, x is 0. We'll see how to work with all of that. And finally, we're also going to find the range. The reason I'm not going to bother with writing down the domain is because all quadratic functions have a domain of all real numbers. I know it seems like a lot, but I'll get you through it. For our first example, sketch a graph of a quadratic function, give the vertex, range, axis of symmetry, and intercepts, all the things that we just talked about. F of x is equal to x minus 3, the quantity squared, minus 10. What I see is that this is a parabola. I know that because of the squared indicator, the fact that there's a quantity squared. That's our basic function. It is translated to the right by 3 units because we remember we change the sign on what's inside the parentheses. And it has a vertical translation that is down 10 units. Because we don't change the sign on what's outside the parentheses. The way we're going to indicate this, we're going to say the vertex is the point 3, negative 10. So let me plot that. And there we have a point 3, negative 10. Looking at the leading coefficient, which looks like there isn't one, it's 1. That indicates to me that there is not a vertical flip. That is to say, this parabola is going to open up. Now let's talk about the range. Because this thing opens up and has a vertex at 3, negative 10, I know that the range is going to be from negative 10 to infinity. That is, the lowest value that this parabola takes on is negative 10, and then it grows up infinitely high. The axis of symmetry is probably more easily considered once we graph the thing. So let's move on to a Y-intercept first. For the Y-intercept, I know that x is equal to 0. And so what I'm looking at is f of 0. In this case, f of 0 is going to be 0 minus 3, the quantity squared, minus 10. In other words, 9 minus 10, and so negative 1. So the y-intercept, if I can rewrite this here just to make it nice and pretty, the y-intercept is at 0, negative 1. I'll plot that. And now what we're looking at is a parabola that has a vertex at 3, negative 10, and goes through the point 0, negative 1. That's enough information to draw a good piece of this, so let's go ahead and do that. And here we have a nice curve from the vertex to that y-intercept. Now enter what we call the axis of symmetry. The axis of symmetry is a vertical line, in this case vertical, in this whole section vertical, that cuts the parabola in half. In other words, from the axis of symmetry, we have this point 0, negative 1, which is 3 units to the left of the axis of symmetry. And so there will be another point 3 units to the right of the axis of symmetry at that same height. And so using that axis of symmetry, I can come up with another dot that the parabola will pass through. And now I can draw a bit more of the parabola. There we are. Now that we've done that, we can talk about the equation of the axis of symmetry. It's a line. It's a vertical line. That means it's going to have an equation that looks like x equals something. And because it goes through the vertex, which has an x-coordinate of 3, it's going to be x equals 3. So I can write that over here in my bookkeeping. For the axis of symmetry, we're looking at x equals 3. There's a tendency folks have to just write down that the axis is 3. That's not right. 3 is a number. X equals 3 is a line. The axis of symmetry should be written as a line. Finally, we can talk about the X-intercepts, for which I need more room, so I'm going to scroll this up, rewrite the original function, f of x is equal to x minus 3, the quantity squared, minus 10. And I remember for an x-intercept that y is equal to 0. I also remember that f of x is playing the role of y. Therefore, I need to solve the equation 0 is equal to x minus 3, the quantity squared, minus 10. If we think back to when we solved by completing the square, we might remember that we did things like getting the quantity that was squared all by itself, which I'm going to do by adding 10 to both sides. So we have x minus 3, the quantity squared, is equal to 10. And then square rooting both sides. Whenever we square root both sides of an equation, we have to remember plus or minus. So we have that x minus 3 is equal to plus or minus the square root of 10, or x is equal to 3 plus or minus the square root of 10. I find it a little bit hard to graph things like 3 plus or minus the square root of 10, and so I'm going to use my calculator to figure out some values here. I'm going to ask my calculator for 3 plus the square root of 10 and 3 minus the square root of 10, just so I have an idea of where I can put dots on the x-axis. And my calculator gave me approximate values of 6.16 and negative 0.16 respectively. That tells me where I can put some dots on the x-axis, and so 6.16, I'm not going to get a high degree of accuracy here, but a little more than 6, and then negative 0.16, that's going to be just to the left of the y-axis there. And we can see that those values are exactly where they belong according to the trend of what we were drawing. I can now write down that the x-intercepts are going to be at, now the x-coordinate of the x-intercepts are what we just found. I'm going to write that down as 3 plus or minus the square root of 10, and of course the y-coordinate is 0. So let me scroll back, is that scrolling up? And I've got now the vertex, the range, the axis of symmetry, the x and y intercepts, and my graph. And that's what this section is going to be about. But our next example isn't quite so gift-wrapped. Here we're given a function f of x is equal to negative 3x squared minus 18x minus 25, and we are asked to sketch the graph, give the vertex, axis of symmetry, range, all that stuff, same as before, and the intercepts. But first we're going to rewrite the function in that form that helps us to see the transformation. In other words, we need to complete the square, but we aren't solving this equation. It's not an equation, it's a function. Therefore, what I'm interested in is just working with the expression that's on the right-hand side. So this is going to feel a little different than completing the square did before, but the broad strokes are the same. I'm completing the square on x, and so what I'm first going to do is focus on the terms that have x. Now, if you remember solving by completing the square, if we had a coefficient on the x squared term of negative 3, we would divide both sides by negative 3. But I don't want to do that with this function notation. I want to leave the f alone. So what I'm actually going to do is I'm going to factor a negative 3 out, but I'm only going to factor it out of the terms that have x, or x squared. When I factor a negative 3 out of negative 3x squared minus 18x, I get x squared plus 6x. Now I'm leaving a little bit of a space inside those parentheses. What I didn't mess with was negative 25. Again, we're completing the square on x, so I was only concerned with x. Now if we think about completing the square with a leading coefficient inside the parentheses of 1, I look at the linear coefficient, in this case 6. We're going to take half of 6, which is 3. We're going to square that 3. It's 9. And we're going to add 9 inside the parentheses. But now we have to think about what's happened. I've added 9 inside of a set of parentheses, outside of which is a factor negative 3. And so what did I really add? What I really added was negative 27. Let's take a look at the expression that we have now. It's negative 3 times the quantity of x squared plus 6x plus 9 minus 25. And all we're doing is we're just exploring one concept right now. If I distribute the negative 3 into the parentheses, then I'll have negative 3x squared minus 18x as before, minus 27 minus 25. Wait, we can simplify. No, that's not where we're going. What we're doing is we're noting the effect that adding a 9 inside of the parentheses had. When we multiply, what that did was it made it so that we have a negative 27. We can't just change this expression by having a negative 27 all of a sudden. So what we've essentially done, what have we really added? We've really added a negative 27. To offset that, what I'd like to have is ultimately I've added 0. That's my goal. And so to offset that, I'm going to add 27. This would be the equivalent of subtracting 27 from both sides and then bringing it over by adding it. But we're not going to be doing that. So like I said, the broad strokes are the same as before, but slightly different considerations. Let me get some of this stuff out of my way here, and we're going to rewrite what we have. What we've just done is we've completed the square, which means we can write this function as f of x is equal to negative 3 times the quantity of x minus 3, x plus 3 squared, and then when I simplify that negative 25 plus 27, it becomes plus 2. Now this should look a little familiar. What I see is that this function is flipped upside down because of the negative 3, and it has a vertical stretch. I also see that because of the x plus 3 quantity squared, it's been moved to the left by 3 units, and because of the plus 2, it's been moved up 2 units. So I have a vertex of negative 3, 2. Let me plot that. Negative 3, 2. And then I see that this parabola opens down because of the flipping. If we consider the range of this parabola, the range, because this parabola opens down, is going to be from negative infinity to 2. In other words, the y-coordinate of the vertex is going to indicate our range. It's going to be one of the endpoints, and we just have to write something appropriate as to whether the graph opens up or down. For the y-intercept, I know x is 0. So what I need to compute is f of 0. In this case, it's easier to look back at the original expression, f of x equals negative 3x squared minus 18x minus 25, and f of 0 is equal to negative 25. Surely you can verify that. It's a little bit out of the scope of the grid that I have here, but I can still write it down. The y-intercept is 0, negative 25. How about the x-intercepts? Well, I know that for the x-intercepts, we have that y is equal to 0, which means that we should be solving 0 is equal to negative 3x squared minus 18x minus 25. There are several ways to solve this, one of which is completing the square, which we've already started. We can take the completed square version, which is also called standard form or vertex form, and write down that we have 0 is equal to negative 3 times x plus 3, the quantity squared, plus 2. And we can solve this as though we had been solving by completing the square, which means I'm going to subtract 2 from both sides and then divide by negative 3 so that I can get the squared term by itself. So I have negative 2 over negative 3 is equal to x plus 3, the quantity squared. Now, as before, we can square root the left and right side of this equation, remembering to throw in the plus or minus. We might be looking at, wait, there's a negative inside the square root. Nope, there are 2 of them. It's negative 2 divided by negative 3. And so what we actually have is plus or minus the square root of 2/3 is equal to x plus 3. And then finally, solving for x, I get x is equal to negative 3 plus or minus the square root of 2/3, which is okay as far as the calculator is concerned. It's not okay as far as writing an answer, because now we have an unrationalized denominator. So I'm going to multiply by 3 over 3 inside the radical, and we end up with x equals negative 3 plus or minus the square root of 6 over 3. Now, as approximations, what we're really looking at is negative 3 plus the square root of 6 over 3, negative 3 minus the square root of 6 over 3, and the calculator is going to give me approximate values, so I know where to put dots on the x-axis. I now have calculator values of approximately negative 2.18 and negative 3.82 respectively. So I'll scroll up and plot those points. Approximately negative 2.18 and negative 3.82. And those are the points that are good enough for me. Those are the points I need to draw this parabola. And I see that this parabola is pretty narrow, as it should be. There was a vertical stretch after all. And we talked before about this axis of symmetry. In this case, the axis of symmetry is going to have an equation x equals negative 3. So that's actually matches the x-coordinate of the vertex. I need to tidy up some of my answers, though. So let me write down that the x-intercepts are negative 3 plus or minus the square root of 6 over 3, comma 0, and then the axis of symmetry is x equals negative 3. So that's all the information that I was asked for. I was also asked to put this into the form with h and k, so I've got that. And you do that by completing the square, generally speaking. And then we were to graph this parabola, which we have done. Next, we're to do all the same things, different functions. So rewrite the function in the form y equals a times the quantity of x minus h squared plus k. Sketch the graph, give the vertex, range, the axis of symmetry, and the intercepts. The function is y equals 1/4 x squared plus 1/2 x minus 1. As you may recall, we're going to do this by completing the square. We're going to complete the square only on x. So the first thing I'm going to do is I'm going to factor the 1/4 out of the first two terms. Factoring actually turns out to look a lot like division. And if I divide by a fourth, that's the same as multiplying by 4. In other words, when I factor a 1/4 out of 1/4 x squared plus 1/2 x, the result's going to be x squared plus 2x. And if you don't believe that, distribute. 1/4 x squared, and then 1/4 times 2 is 1/2. See, told you. There was a constant term of minus 1, and that's still going to be there. Now, inside the parentheses, I want to complete the square. So what I'm going to do is I'm going to focus on that 2. Cut it in half, square it, I'm adding 1. But now it's that game. What did I really add? I really added 1/4 times 1. So I really added 1/4. To offset adding 1/4, I need to subtract 1/4. Ultimately now, what we've done is we've added 0. Note that as it was in the previous example, so it is in this example, that the thing we added, that negative 1/4, has a sign that is opposite that 1/4 that is the leading coefficient. Now these won't always be the same numerical number. I mean, last time it was, negative 3 and then a 27. But these do have opposite signs. And that's the result of the coefficient interacting with what we added in the parentheses and then offsetting. So the leading coefficient and the offsetting thing will always have opposite signs. Now back to our regularly scheduled programming. Now I've got y equals 1/4 times the quantity of x plus 1 squared, because we completed the square, minus 5/4 when I combine negative 1 and negative 1/4. From this form, I can get the vertex pretty straightforwardly. The vertex is negative 1, negative 5/4. I can go ahead and plot that, negative 1, negative 5/4, in the third quadrant there. And this parabola opens up because of the 1/4 as a leading coefficient. It's not negative, and it's going to be quite wide. We can talk about the range. Because it opens up, the range is going to be negative 5/4 to infinity, and these are always a square bracket at the numerical value of the range. The Y-intercept, generally one of the easier things to find. Remember, the Y-intercept is where x is 0. If x is 0, then the first term is 0, the second term is 0, and I pick up just the negative 1. Therefore, the Y-intercept is going to be 0, negative 1. I can plot that point there, and then I can use the symmetry to plot the point negative 2, negative 1. We could connect the dots here. I guess I'm going to go ahead and do it. Seems to me that this is pretty wide. And we're going to confirm that what we've drawn is somewhat okay by looking at the x-intercepts. But first, we're going to talk about that axis of symmetry. Cuts the parabola halfway through the halfway through itself, right down the middle. And so I'm going to leave a space for the x-intercept. The axis of symmetry is going to be x is equal to negative 1. It's got the same x value as the vertex. And then the x-intercepts. Remember, the x-intercepts are where y is equal to 0. And so we're going to solve the equation. 0 is equal to 1/4 times the quantity of x plus 1 squared minus 5/4. And so, adding 5/4 to both sides, I get 5/4 equals 1/4 times the quantity of x plus 1 squared. Clearing the fractions by multiplying by 4, I get 5 is equal to x plus 1, the quantity squared. Square rooting both sides, I'm flipping the thing around too. We're going to get x plus 1 is equal to plus or minus the square root of 5. And finally, x is equal to -1 plus or minus the square root of 5. I'm going to go ahead and write the x-intercepts down like that. So the x-intercepts are -1 plus or minus the square root of 5, comma 0. Remember, intercepts are points. They're not just numbers. But to know where to plot them, I'm going to use my calculator. So I need -1 plus the square root of 5, -1 minus the square root of 5. Are they any nice numbers? Sometimes. We just happen to have a few that aren't. My calculator is telling me that these values are 1.24 and -3.24 approximately, comma, respectively. And so I'll plot 1.24 and -3.24. Looks like I missed it by a hair. But this is, oh, fine. Let's erase that part of it then and redraw it so it goes through the point approximately -3.25, 0. Oh, I might as well extend the other one, make it look nice and pretty. And there we go. Notice this parabola is quite wider than the last one, and that's due to the vertical compression that we have from a factor of 1/4. But there we have it. We've put the parabola's equation in the form that we needed with h and k. We've got our vertex, our range, our axis of symmetry, and our intercepts. And we drew the graph. I want to talk just briefly about the x-intercepts. Suppose I had a parabola with a vertex that was above the x-axis and it opened up. There are no x-intercepts. Or if I had a parabola, the vertex was below the x-axis and it opened down. Again, no x-intercept. What you would find is if you were trying to solve these, you would end up with complex solutions. And so these are kind of pictures that tell you what complex solutions look like, or where they come from, kind of. But it's also the case that if you try to solve a quadratic equation or try to find the x-intercepts and you get complex solutions, there are no x-intercepts. It would be appropriate to write x-intercepts none.